Okay, so one of the advantages of defining these transforms, the Q transform of a convolution kernel, is that we have this sort of representation um, of sinusoids in terms of how a sinusoidal input is mapped through a linear system. And one of the interesting observations about this, and this is, of course, for some of you who have learned some of the stuff before, is that we always think of the interesting property that if you put a sinusoidal input, like a sine, cosine, or combinations of the two, you actually get another combination of a sinusoidal signal. That in fact, sinusoids are what are known as eigenfunctions. Eigenfunctions, if you think about a matrix, an eigenvector of a matrix is one where eigenvector of a matrix is when if you apply A times X, you get lambda times X. We call that an eigenvector because the vector is just scaled at the output, right? Of course, linear systems are an exaggerated version of a matrix. They're just an infinite dimensional matrix. So what are the eigenvectors of a linear system? They are actually the exponential complex function. And so we are going to try to verify that and use that as intuition. So the point is, we think of what I'm going to do is I'm going to do the computation for an input that looks like a cosine omega naught t. And by the way, a cosine can be viewed as the real part of e to the I omega t. Remember, if you don't remember this, e to the I omega t is nothing but cosine omega t plus I sine omega t. It's a complex quantity that has this particular real part and this particular imaginary part. Okay? Because of linear systems, if you put in cosine omega t plus I sine omega t, then the response is whatever responds to this part first, and then I plus the response of that second part because of linearity. And so then, then what we observe that all we have to do is take the real part of the output to find the real part of the input. So it's kind of like a nice manipulation of the properties, using the properties of linear system theory. Anyway, this is gonna all become very clear. So I'm going to actually now do the computation for an input u of t, equals to e to the I omega t, e to the minus I omega t, and I'm going to try to see what the output y of t is. Remember now, G is the linear system that I'm operating with, and it corresponds to a convolution kernel I'm going to call G, little g of k, right? So the output, y of t, is going to be the summation from k equals minus infinity to infinity, g of k, e to the minus I omega of t minus k. That's the formula that we have for convolution. Simple manipulation, I can write this as e to the minus I omega t times the summation over k, g of k, e to the minus becomes a plus I omega k. That's just by taking out the expression that doesn't depend on k. And now, what do we observe? What is this expression over here? But that is nothing but the Q transform of that system evaluated at e to the I omega. So this quantity over here is e to the minus I omega t times g of q evaluated at e to the I omega. Or I can write it up as equal to e to the minus I omega t times g of e to the I omega. Okay. What is nice about this is that we are, proving in a way the property of the eigenfunction. We start with an input, which is an exponential, and that exponential is this one over here. We observe that the output has the same input, e to the minus I omega t, okay, minus omega t, times a constant, a scaling quantity that is represented by G, evaluated at e to the I omega. We often refer to this quantity here as frequency response. Why? Because if the claim here is that complex exponentials, which is sines and cosines, are eigenfunctions of this linear system. You pass it on, and what you see at the output is an output of the same frequency, but scaled and changed in a particular way. It's scaled and shifted in a particular way. That scale and shifting is happening through the frequency response, which is a complex quantity. You're multiplying this by a complex quantity, okay? So now if you actually thought about the actual input u of t being equal to cosine omega t, that is equal to real part of e to the minus I omega t, okay? Because it's equal to the real part of I omega t, then the output that I'm looking for, y of t, is going to be the real part of e to the minus I omega t, g e to the I omega, right? That's what we see as the outcome of this sinusoidal input. So from a simpler point of view, it's better to think of the exponential function, the complex exponential, as in itself the eigenvector, the eigenfunction. It is a function that if you pass it through a linear system, it comes out with the same frequency. The frequency, of course, is the W over here. And the frequency of the output is the same W, but the way it's scaled is through the transfer function, the Q transform, which we call a transfer function, multiplying it and adjusting it in terms of magnitude and phase. It multiplies it by something and it changes the shift after you take the real part of that quantity. That's an important thing, and it motivates for us to think, when we think about linear systems, in terms of a frequency response. We often think about the frequency response. A lot of older engineers always think about linear systems in terms of frequency plots. They don't think about the actual convolution kernel. They just see what that system does for every frequency. Does it amplify that frequency? Does it reduce that particular frequency? And the whole filter design in the world of digital signal processing is entirely based on this frequency response analysis. And it's not inseparable from a lot of the stuff that we want to do when we study time series analysis. So this is the formal proof that was written for you over here. Okay. So now that I've described explicitly that the frequency response of a sinusoid is a sinusoid, that sinusoidal functions are eigenfunction, there's a slight subtlety that happens to us often when we don't look at things that start from minus infinity to infinity, but we look at things that start from 0 to infinity. So what happens if the input is a sinusoid that starts from 0 to infinity, but not from minus infinity to infinity? What do I see at the output? Well, I would like you to calculate that. And so what you want to do is now, and I would just say that your y of t now is, as before, equal to the summation from k equals minus infinity to infinity, g of k, okay, e to the minus I omega of t minus k. But now because I'm saying the input was 0 from t negative, this summation has to go up to t only. It cannot go all the way to infinity, so it has to go up to t. You can play the same game and take out e to the minus I omega t, and you're left with summation from k equals minus infinity up to t, g of k e to the I omega k. The problem is that this expression over here, this expression, is not exactly the Q transform or the transfer function evaluated at e to the I omega k. It is there up to value t. So we're missing the part that goes from t to infinity in order to define the transform. Okay, so one way to do this is I can write this as e to the minus omega t and write this as summation, okay, from k equals minus infinity to infinity, g of k e to the I omega k, but subtract the part that starts from k equals t plus 1 to infinity g of k e to the I omega k. See what I'm saying? So I am now representing the summation from minus infinity to t as the actual Q transform, but subtracting a piece of that is not in the expression. Now this is going to be e to the minus I omega t times g of e to the I omega. So that's good. That's the same expression that we had before, but we're subtracting another part over here. The question, how big is that part? And that part, as you know, from the stability argument, it's starting from k equals t plus 1. So if t is large, this quantity here is going to be actually small. Why is it going to be small? Because g of k is absolutely summable. So if you sum the tail of it, it's going to be very, very small. Okay? So that's the argument that says what I'm seeing is the same thing as before, the same eigenfunction argument, a scaling of the input times g, but then there is a transient part that disappears as t increases. Okay? And that transient, you know, is essentially a part that we can ignore, or we can actually keep, but we don't really worry about it too much. So this transient part goes to 0 as t goes to infinity. This is the expression over here that I just wrote down. And you can rewrite all of this in terms of the real part. I kept it in terms of the exponential, but you can write it in terms of the real part. And again, we have this part that is disappearing because we're summing from t to infinity. So I'm jumping here with the expression that I already have provided for you, but you should verify that, in fact, as I said before, what you see is the value of the scaling of the sinusoid. We often refer to this as the steady state function, and then we see a part that is disappearing as a function of t. Okay? So that's what happens to us when we start something from 0 as opposed to starting from minus infinity. It's a technicality, but exponential functions are eigenfunctions when you start them from minus infinity to infinity. They are not eigenfunctions when they start from 0 to infinity. There is a transient part that has to be taken into consideration. Okay.